Welcome back to the lab. Today we're going to introduce the concept of stability in control loops. This is going to be an important concept moving forward throughout Project Darwin, since we need our control loops to be stable in order for the regulation. The essence of stability is very simple. If something is too big, make it smaller. If something is too small, make it bigger. Let's say we want to make a voltage regulator. To maintain a constant voltage, which is what voltage regulators do, we need to monitor the output voltage and correct for any measured error. In order to determine the difference between what we want and what we have, we need a reference to compare the measured output voltage to. In most cases, this would be a band gap reference, which is a temperature compensated voltage reference commonly used in integrated circuits. Then you scale down your measured voltage to compare it to it, and then that's how you know where you are with your output. Now, this is the critical part. If we really want to make voltage regulation happen, we need to increase the output voltage by supplying more current when the output is too low, and then decrease the voltage by supplying less current when the output voltage is too high. This principle of turning something down when it's too large and turning something up when it's too small is called negative feedback. Ensuring stability is very similar to ensuring that there is always negative feedback. It's also important that the control loop has enough bandwidth and responds fast enough to the oscillations that may be present in the system so that it doesn't lose track of that situation. If the control loop is too slow, this usually manifests as oscillation on the output, excessive overshoot, and/or slow response times. Stability is important, but it isn't the whole story either. Ensuring stability doesn't mean that the control loop will regulate voltage well, or that it will respond how you want to at all. However, ensuring stability does mean that your voltage regulator won't oscillate wildly between the maximum and minimum input voltage when you poke it with a stick from 10 feet away to turn it on. There are a lot of different methods to determine stability, depending on what your system looks like. There are versions for linear systems, nonlinear systems, bounded systems. Some methods are more experimental and others are more theoretical. We could dive pretty deep into calculus and transformations if we really wanted to, but that doesn't sound like very much fun right now. Instead of all that, let's talk about how stability relates to our inverter project called Project Darwin. In this case, the system we need to control is the output filter for the system. Why do I want to control this without adding a load to the plant? Well, this is for two reasons. One, the main reason is because our load is not well defined, and the other reason is because I expect the output voltage ripple on the output to be a maximum in the no load condition, so it should be the worst case. Regardless of why, I took the output filter circuit and performed a Laplace transform to bring this circuit into what is commonly known as a transfer function in the S domain. Plotting the step response, or how the system responds to a step change on the input, describes a few things about how the system behaves. In this case, the step response shows a wildly unstable response and ringing with a magnitude of 1.5 times the desired voltage. This is completely unacceptable. Not only does it make me cringe, it would also result in an overshoot of 1.5 times the set point. So in other words, if a system was designed to output 120 volts AC, it would hit a peak output voltage of 180 volts. Nope, not gonna work. Let's get this under control. Oh gosh, that was bad. But after tuning the response of a controller to compensate for the load, you can see that we can keep the overshoot reasonable and settle out to the desired voltage set point within a few cycles. Okay, that looks great on the computer, but how do we get this into our micro? Well, that's kind of tricky. Let's walk through the conversion process, from circuit to executable function. It's not an easy road. That's pretty bumpy, in fact, but it is possible to get there. I don't really expect that this will make sense to everyone, since each of these steps would be described in its own college-level class or two, and describe multiple years of calculus knowledge to even get into that class. Consider this more of an overview. I want to give you some words that you might need in order to dive into one of these concepts in more detail, or even all of these concepts. In order to get this control loop on the micro, I started with the Laplace transformation, as described before. This brings the circuit transfer function into the S domain. This is where I tuned the compensation network, which gave me a complementary transfer function that when multiplied with the transfer function for the plant in the S domain results in the tuned response you saw earlier. I believe this is equivalent to convolution in the time domain. Now this is where things get a little freaky. The S domain is continuous time, so we would need to build our controller out of analog components like op-amps. Don't lose hope though. If the S domain is translated into the Z domain, where an assumed sampling time is baked into the equation, we can then take this Z domain transfer function and convert it into a difference equation. At this point, all terms of our compensator will be represented as a function of the error signal, which is the difference between where we are and where we want to be. Some compensators require past or future samples to be considered in this difference equation, so it may be necessary to store a few previous versions of the error signal for this controller to function correctly. Let's take a small breather here. That was a lot to digest. I firmly believe that if a person like you is dedicated to learn something, having a teacher is really not necessary. Being in a college level class is not necessary. If you want to learn about this stuff, the information is online. Grab a textbook about Laplace transforms, digital signal processing, and control systems, and don't stop until you understand. I've also found a couple books online that look great. It cost around $20. You really don't need the current edition either. Control systems and this math hasn't changed in a very long while. So if all this math is getting you down, and you don't want to dive into all these textbooks, there are less math-heavy methods to getting a working control loop, and this is done by measuring its performance through characterization of the step response or evaluating gain and phase margin. Why do we care about the gain and phase of a system anyway? Well, it's because if the system is designed to have negative feedback, remember, turn it down when it gets too high, turn it up when it gets too low, but the phase shift of that system is 180 degrees, that's the same as multiplying by -1, so we'll go from turning it down when it gets too high to turning it up when it gets too high. That'll just keep getting bigger and bigger till something breaks or the limit of the system is reached. Gain and phase margin ensure that we have negative feedback at all frequencies when we design a system to be stable when there's negative feedback. Gain margin ensures that if we hit a point where there is that 180-degree phase shift, the control loop is making the signal smaller, so oscillations cannot build or it's attenuated. This means that the amplification ratio, or gain, is less than 1. Gain margin is a measure of how small the amplification factor is at that critical point, and the more gain margin the control loop has, the better. Similarly, phase margin is a measure of how close we are to a phase shift of 180 degrees, when the gain of the controller is 0 dB, or an amplification ratio of 1. Again, bigger is better. To try and rephrase that, gain margin and phase margin describe how close we are to the critical point of marginal stability, where gain is 1 and phase shift is exactly 180 degrees. This can be experimentally measured by breaking the control loop, injecting a known input signal into the controller at a frequency, and measuring how it responds. In order to evaluate gain and phase margin successfully, you need two things: the transfer function of the plant, or the thing being controlled, and the transfer function of the controller. The transfer function of the plant and controller get combined to create a system transfer function. This plot of phase and magnitude in degrees and decibels respectively, with respect to frequency, this is commonly known as a Bode plot, or Bode plot, and is a standard tool used in electrical engineering. As a note, it's possible to not be stable or unstable, but rather somewhere in the middle. If phase margin and gain margin are positive but really small in value, that means the controller is operating right on the brink of instability. Being on that edge of oscillation means that there'll be some damped oscillations in the system, but probably more than a person would like, even though it's technically stable. Therefore, it's important to maximize gain and phase margin to ensure that the system is stable rather than quasi-stable. Control systems and tuning controllers gets pretty math heavy really fast. While there's only so much one can talk about in 10 minutes, I hope that I said enough of the keywords to show you how the different transformations link together and empower you to pursue these concepts in more depth. If you feel like you're left with more questions than answers right now, leave those questions in the comments. Let's get some good discussion going and point you in the right direction to find some good resources. We talked a little about how we are starting to evaluate stability for Project Darwin, and talked about why that is critical to our project success. Now we're ready to move forward. We're working our way through the proof of concept phase of Project Darwin, or our inverter project. Stay tuned for our future videos where we'll assemble our proof of concept board and test it out. I think that stability is great. If you think that math is hard and inverters are awesome, let me know by hitting the like button on this video, subscribing to the channel, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye!